If you remember from earlier, I showed you a Venn diagram similar to this, where this red circle represents everything that's in set A, and then everything outside of the red circle that's in the sample space is actually, we call that the complement of A, or A prime. Now actually, it's a very simple way to get a formula for the complement. Now I probably should have used E here instead of A, because when I get down to the formula I use E, so it might be a little bit confusing, but I don't think it's too terribly bad. First of all, you know that if you intersect the set A with the set A prime, there's obviously no overlap, so that set's empty. And you know that if you were to take the union of those two sets, that would give you the entire sample space, because A prime plus A gives you everything that's in the rectangle. So the number of elements that's in A union A prime would be the same as the number of elements that's in the sample space. So then therefore we could say that the probability of A union A prime is the probability of getting something in the sample space. And since the probability of the sample space is always equal to 1, because the probability of getting something in your sample space always has to equal 1, then therefore the probability of A union A prime must equal 1. And then let me show you one other formula that you... So since A and A prime do not intersect, from the property we just talked about, we know the probability of A union A prime is simply the probability of A plus the probability of A prime. But down here, since we also know the probability of A union A prime is the probability S, which equals 1, then we know the probability of A plus the probability of A prime must equal 1. So when I put this in a formula, I actually used E, since E is usually used for an event. So the probability of an event E plus the probability of E prime, not the event, always has to equal 1. And so since that statement's always true, we can actually solve for the probability of E in terms of the probability of E prime using just some simple algebra. So the probability of E is 1 minus the probability of E prime. But you can also solve for the probability of E prime the same way and say the probability of E prime is 1 minus the probability of E. Now, sometimes you can calculate the probability of a complement without using these formulas, but other times it's actually very nice to have this formula because it'll save you the work, because sometimes it might be easier to calculate one of these over the other, and then if you calculate one of these, then you can easily find the other using these formulas here. So let me give you some simple examples. Let's say 2 dice are tossed. What's the probability the dice will be different numbers? Well, we know that there's 36 possible elements in the sample space, and let's say that A is the event that the 2 dice are different. Now that's what we want to find. But A prime would be the event that the 2 dice are not different. In other words, they must be the same. Well, it's easier to count the number of ways that they can be the same than it is to count the number of ways they're different. So it's easier to calculate the probability of A prime. So the probability of A prime, there's 6 ways they can be the same or not different. And so the probability of that would be 6 out of 36, which is 1/6. So now if you want to find the probability of A, just do 1 minus the probability of A prime, and 1 minus 1/6 is 5/6. Another example says, suppose 2 fair die are rolled. Find the probability that the sum of the numbers rolled is greater than 3. Well, let's let A be what we're looking for, the event of a sum greater than 3, and there's of course lots of ways this can happen. But let A prime be the event of a sum not greater than 3. Well, there's only 3 rolls that are not greater than 3, a 1-1, a 1-2, or a 2-1. So there's 3 ways that can happen. So the probability of A prime would be 3 out of 36, or 1/12. So now to find the probability of A, just subtract that from 1, And so 1 minus 1/12 is 11/12. Now those examples could have been solved without using the complement, but this next one is not one that you'd want to solve directly. You'd actually want to use the complement on this one. 8 cards are drawn from a standard deck. What is the probability of getting at least one face card? Well, we know that the number of 8 card hands is 52 choose 8, so we'll hold on to that for later. Let's say E is the event of getting at least one face card. Well, that would mean you get either, that would mean all the hands that have exactly one face card, 2 face cards, 3 face cards, 4 face cards, 5 face cards, 6 face cards, 7 face cards, or 8 face cards. Now, to calculate this directly, it would be very difficult because you would have to calculate each one of these 8 probabilities and add them together. But if you think about what is the complement, what is the event of not getting a face card, that would be the complement. In other words, 0 face cards would be the complement. It's much easier to get the probability of getting no face cards. And so let's do that. The probability of getting no face cards would mean out of the 12 face cards choose none, and out of the 40 other cards choose all 8, and then divide that by 52 choose 8 to get the probability, and I get 0.1022. And then if you subtract 0.1022 from 1, then that will give you the probability of the original question. The probability of getting at least one face card is 0.8978. The birthday problem is a classic probability problem, but probably not at the level to explain to a freshman or sophomore class. But the results are certainly interesting. How many people would you randomly select in order to expect there to be a 97% chance of 2 or more having the same birthday, excluding twins? Well, if you view this video here, this gentleman does a very good job of explaining the birthday problem. But it turns out there's a formula that you can develop, and the formula is developed not by finding all the ways that 2 or more people can have the same birthday, but what it does is it finds the number of ways, it finds the complement, it finds the probability that no 2 people have the same birthday. So if you find the probability that no 2 people have the same birthday and subtract it from 1, then that'll give you the probability. So don't worry about trying to figure this out, but the formula for the probability that no 2 people have the same birthday with a group of n people, n randomly selected people, that probability would be 365 factorial divided by 365 to the n times 365 minus n quantity factorial. And then if you know that probability, then you can get the probability of 2 or more people having the same birthday by just subtracting this from 1. And if you do this calculation for 30 students, you get the probability that 2 or more have the same birthday is about a 70% chance, 0.71. And so it really only takes around 40 students to get up to the 97% chance of 2 or more having the same birthday. It might be 50, but it's around 40 or 50 students to get a 97% chance. I'm just going to slowly scroll through developing the formula for the birthday problem, and there's more than one way to develop this formula, so the method I use here is not actually the method the guy used in the video, but again, you don't really need to know this. This is this is what I would call higher math, but anyway, you can see that I calculated the formula down here. So here's the formula for the probability of no 2 people having the same birthday, and then of course if you subtract it 1, you get the probability that 2 or more have the same birthday. Yeah, there's the answer. So yeah, it takes 50 people to get a probability of 97% chance of 2 or more having the same birthday. Now, what's interesting is even if you have 100 people, you only get up to 99.999997% chance. The only way to get a 100% chance birthday is to have 366 people, because in that case then you would know that you've got every birthday covered at least once plus one more. Of course, we're ignoring leap years. One last problem on this. A shipment of 45 cell phones contains 9 that are defective. The Quality Control Department random selects 10 phones from the shipment and tests them. The shipment is rejected if at least one of the sample is found defective. What is the probability the shipment is rejected? Well, what we need to find out is the probability that we have at least one defective. Now, remember a while ago I showed you that the way to calculate this, rather than try to find the probability that at least one is defective, let's find the probability that we have none defective and then subtract it from 1. So the number of ways to have none defective would mean out of the 9 defective phones we chose none of them, and out of the 36 good phones we chose all 10. So the probability of none defective would be 9 choose 0 times 36 choose 10 over the total number of samples possible, which is 45 choose 10, and that's 0.08. And then to calculate the probability that at least one is defective, we simply subtract this from 1. So 1 minus 0.08 is 0.92. And so that gives you a 92% chance that the shipment is rejected. That finishes the section on probability of a complement. In the next section, I'll talk about odds and how odds relates to probability.